Anyways, no, I don't need you, nigger.
Hello, my name is Andre, and I've been training deep neural network.
Experiment, get uncomfortable, teach, repeat. That's the whole video.
Thank you very much for coming.
Experiment, get uncomfortable, teach, repeat.
Anyways, I'm going to read all of these books, do one or two projects, and get incredibly compensated for my incredible skills. Anyways, pam, 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 pam. What was I asking? So labeling, there's a lot. Obviously, there's a lot of human error. So the way we categorize data has a lot of presuppositions. For example, when we label someone as you're an engineering major, you're a humanities major, you're an English major, it has a presupposition that they never did, they don't have any hobbies, they don't have any sort of social interaction with people who are like engineers. They don't share a roommate who is like a quantum physicist that might kind of like tingle their senses with science, right? So we're making all of these presupposition just because. So that's an issue with sam. I mean, that's an issue with labeling and sampling and labeling, right? We are just labeling them as you're just engineering student or you're just humanities students. But then if you like dig down deeper, the engineering student might reach a lot of Sherlock Holmes or shit like that. So depends, depends for sure. mlops is anyways sampling. Sampling is an integral part of an ML workflow. Unfortunately, often overlooked in typical ML coursework. Sampling is happens in many steps of ML project life cycles, such as sampling of all possible real-world data to create training data, sampling from a given data set to split for training, validation, and testing, or sampling from all possibility events that can happen within an ML system for monitoring purpose. Okay, we are sampling to like do some sort of a monitoring purpose or like to like actually build the model. Cool. In this section, we'll focus on sampling methods for creating and training ML models, but these sampling methods can also be used for other steps in the ML production lifecycle. Okay. You can use another section like for monitoring and whatnot. In many cases, sampling is necessary. One case is when you don't have access to all possible data in the real world. The data you have to train the model is a subset of the real world data set. Okay, that is a huge issue with sampling too. Especially, it's like, let's say you want to get an opinion on how university. It's like you don't like ask every single. That's going to take a lot of time and resource and energy. So you can do something called sampling, and that kind of like I mean, you need to be intelligent with it. So that's the thing with like studies. It's like if you don't know how to interpret these sampling, you can easily like kind of like manipulate the data to like fit whatever the fuck you want to do. So yeah, let's say in many cases sampling is necessary. You have to access understanding the different sampling method and how they're being used can work. First, help us avoid potential sampling bias. Second, help us choose the method to improve efficiency of data we sample. Okay, first is like we need to like understand what are the best way to like sample so that you can cut the most cost, right? It's like sampling Miami girls isn't the same as the sampling of, I don't know, Texas girls. They're going to be more conservative and all of that. There's a sampling thing. Okay, anyway, there are two families of sampling: non-probability sampling and random sampling. We'll start with non-probability. The thing is, it's assuming random sampling, but random sampling is basically impossible. It's there's always going to be some sort of patterns emerging, right? You try to like, okay, let me get like a random woman off the street. You're not getting a random woman off the street. That's like a saying. It's a literary saying. It's not actually you're not actually randomly selecting women off the street. You're randomly selecting women from Salisbury that happens to go on a certain road that you choose to do it. So it's not actually random. It actually has more order and more what you call it. It's more orderly than you like to assume. It's not as chaotic as you think. Okay. Anyways, there are two families of sampling followed by several common random sampling methods. Non-probability. Okay. Non-probability sampling is when the section of data isn't being based on any probability criteria. Here's some criteria for non-probability. Convenience sampling. Sampling of data are selected based on the availability. This sampling method is popular because it's convenient. Here's the thing. It's like we need to like take back like heroin works, right? We know heroin works because we know it's not a placebo effect. We can control it for a placebo effect, whatever. But heroin works. But here's the thing: is it a preconceived? If someone who never, if you slip heroin, let's say someone is like sniffing white chalkboard instead of, will they get high? They didn't know. They will get high. They will get high, right? And we're making, I don't know, like instead of chalk being made of like calcium, we are like kind of like switching it for cocaine. And every time they kind of inhaling it without knowing it. And that's the kind of question we're asking, which is, the placebo is good. Yes, we know heroin. It doesn't matter what kind of placebo you take. It's gonna you can control the placebo however you want. I mean, that will be like the ideal experiment to make, but it's kind of like really unethical because you're just randomly drugging a guy. But you can kind of like have this kind of reasoning where, okay, someone is like smoking a weed. Okay, someone is eating a chocolate that is like a brownie wheat chocolate or something, right? A wheat brownie. They're gonna get high. It doesn't matter like whether they know it has weed in it or not. They're gonna get high. So we know based on that. It's not like it's not really like a placebo kind of thing. So so again, it is real. I have to like prove it to myself, anyways. Convenience of sampling. Sampling data are selected based on the availability. This sampling method is popular because it's well convenient. Snowball sampling. Future samples are selected based on existing samples for For example, to scrape legitimate Twitter accounts without having access to Twitter database, you start to follow a small number of accounts, then you scrap the account based on who they follow and so on. Okay, whatever. Oh, it's like a graph neural network. I mean, what is it called? Nodes and edges type of stuff. Okay. Judgment sampling. Experts decide what samples need to include. Okay, what the fuck? I'm the expert, nigga. Fuck. Anyways, quota sampling. You select the samples based on the quotas for certain slices of data with randomization. For example, when doing a survey, you might want 100 responses from each of the age group under 30 years old. So I need 100 responses from each age group under 30 years old, between the ages of 30 and 60, and above the age of 60, regardless of the actual age distribution. Okay, we're making some sort of arbitrary quota to get their opinion. I mean, yeah, it can, like, why is the reason? Like, do we want to report it as, like, between ages of like 22 to like 28 makes this much money? That would be like pretty like reasonable to assume. But we do have like full data sets for that though. The samples selected by non-probability criteria are represented by real-world data and therefore are riddled with selection bias. Of course, it is a selection bias thing, of course. Because these biases, you might think it is a bad idea to train an ML model using a family of sampling tree. You're right. Unfortunately, there are many cases of selection data ML models are driven by convenience. Yeah, it's just like convenient, isn't it? It's like, of course. Yeah, it is convenient, anyways. One example of these cases, large language models are often trained with not data representative of a possible text, but the data can be easily collected. Wikipedia, Common Crawl, Reddit, and whatnot. Another example is data as a sentiment analysis of general text. Much of this data is collected in the source of natural labels, ratings such as INB review and Amazon review. The data sets are used in the sentiment analysis
Works
tasks
for a
and
bit more than a decade.
okay,
And in
okay. These data are used in sentiment analysis tags, IMB checks, reviews, and analysis based on the users are willing to leave an online review necessarily not represented out. Okay, you could just, yeah. Okay, sentiment analysis is actually trained by Amazon reviews and all of these reviews, and they would like use certain keywords. And let's say it's like a 1-star review, and they're like, "This sucks. I need refund. This is horrible. This product is bad." It's not. You can kind of map that with sentiments, and this is excellent would be like a 5-star. So you can kind of like mathematically kind of label them in that way. Yeah, it's a cosine similarities, right? You can like plot all of those bad reviews in a three-dimensional space, all of the medium reviews. So it's literally like in a ball of, it's the good reviews are here, bad reviews. So you can literally see how similar the words are with each other and whatnot. And that's how they did. Sentiment analysis started off as some method like that. I mean, obviously, it's not like 100% perfect. Nothing in the world is like 100% certain. It's impossible. It's impossible. You know, if it is 100% certain, it's God. Okay, it's God. We could just call it God. Whatever is 100% certain, it's God. And a lot of people think AI is just this personal friend. Stupid. Because it's just like bunch of cosine similarities. You're just talking to some numbers. In a simple random sampling. In the simplest form of random sampling, you give all sample of in the population probabilities being selected. For example, you randomly select 10% of the population, given all members of the popular 10% equal chance of being selected. That what the fuck am I looking at? The advantage of the method is easy to implement. The drawback is that the rare category of data might not appear in the selection. Consider the case where class appears in only 0.01 on population. If you randomly select 1% of the data, samples of this rate is unlikely to be selected. Models trained on this selection One thing is rare class doesn't exist. I wanna fucking beat the fuck out of you. Fucking. Anyways, stratified sampling. To avoid the drawback of sampling random sampling, you can while you care about the sampling each group separately. For example, 1% of the sample data has two cases, A and B. You can sample for 1% in A, 1% in B, and they know this in this way, no matter how rare A and B, you ensure the sampling is complete. Each group is called stratum weighted sampling.
Hmm.
Sampling techniques. This time we're going to talk about stratified sampling. And last time we talked about SRS, or simple random sampling. We're going to use that in our stratified sampling. Now, this is not called SS, it's just stratified sampling. I've got the same population as last time. Let's say these are my dog walkers or my voters, whatever they may be, and I still want a sample size of, this time let's say I want a sample size of 12, okay? So what I end up doing in stratified sampling is I want an equal or close to an equal amount of people from each group of people. So the first thing I need to do is group these people. So I'm going to put all of my blue guys over here, and I'm going to put all of my red ladies over here. This will take a couple minutes to do, but what I'm doing is I am putting them into groups, and I'm grouping them by some kind of characteristic. In this case, I'm grouping them by color and the way that they look. And I hope that doesn't sound like I'm discriminating against anybody or profiling or anything. That's not what I'm looking to do here. I'm just grouping them by a characteristic, and the characteristic that I decided to go with is the way that they look. Almost finished here. Let's take all of these and move them down a little bit. Move this guy up here with his group. And there we go. Now, each one of these groups is called a strata. So this would be my blue guy strata, this would be my black guy strata, this would be my red girl strata. Each one is a strata. They are grouped by some kind of characteristic. So I have stratified them, or put them into strata. Now comes the time when I use SRS, simple random sampling. I want to get 4 people from the blue strata, 4 people from the black strata, and 4 people from the red strata, so that I can create my sample size of 12. Well, if I use SRS, what I then do is number each one, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 for my blue. And I number these guys here, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And then I also number the girls here, 1, 2, 3, 4, 5, 6, 7, 8, 9. Did I skip over one? 1, 2, 3, 4, 5. Oh, I numbered too many here. Let me start that over. Nothing wrong with making mistakes. 6, 7, 8, 9, and then here's number 10. I would then use SRS for each group. I don't want to use the same numbers for each group, so I want to use SRS for the blue group. And I would choose, let's say the numbers that came up for the first group were the numbers 2, so I'm going to interview this guy. 7, I'm going to interview this guy. 5, so I'm going to interview this guy. And 10, interview this guy. Now I'm not finished with my sample because I want a sample size of 12, so I've got 4 from this strata. Then I go over to the black strata, or the group of black characters. So here we go. I would use SRS again, and the numbers that come up are 7, so I'm going to interview him, and 4, and I interview him. 10, I'm going to interview him. And then 7 comes up again. Now, do I interview 7 again? No, I just skip over that number. It'd be pointless to interview number 7 a second time. So I continue to randomly generate numbers or draw numbers out of a hat for SRS, and the next number that comes up is 1. So I'm going to interview this guy. Well, I've only got 1, 2, 3, 4, 5, 6, 7, 8 people for my sample size. Now I go to my red group, or my red strata, and I use SRS to get 4 more people, or randomly choose 4 more people from this group. And in this group I get number 3, so I interview her. Number 9, I interview her. Number 10, I interview her. Number 3 comes up again, so I skip it. And then number 6 comes up, so I interview her. And I have now got my 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 people for my interview, and I have a sample size of 12. Simple random sampling is used for each group. Each group is called a strata, and that is stratified.
Yeah, arbitrary. Like, it's not random though. I mean, kind of is, but anyways. Weighted sampling. In weighted sampling, each sample is a given weight, which determines the probability of being selected. For example, you have three samples, A, B, and C, and you want to be selected with the probability of 50%, 30%, 20%, respectively. You can give them the weight of 0.5, 0.3, 0.2. This method allows you to leverage domain expertise. For example, if you want to know what's subpopulation of the data, such as the most recent data, is more valuable for your model. If you want higher chance of being selected, you can give a higher weight. Okay, this also helps the case and data distribution compared to true data. For example, okay, whatever. Um, Sampling, boring. Anyways, shook, duplicate. Sampling, class imbalance, data augmentation. These are the training issues. I mean, yeah, labeling always has issues because some labels are ambiguous. You can't really classify. I think this is like philosophical debate of can you label things? Can it be labeled? Can humans be labeled? Can emotions be? Kind of can be, but it's like that's more of a semantics thing than it's like a literal. I mean, listen, semantics kind of influence the way we think. Noam Chomsky kind of proved it, but it doesn't matter. It doesn't matter. It's still like kind of complex unless you're talking to a guy extremely dumb who can think. Like it's like here's the thing. People think the neural networks they can't understand words. I mean, people think they understand the real world. That's we're it can't even process language. And I have a guess with the probabilistic method that we train models. It can never. It's basically guessing. It's guessing the next best output. And how can it ever? It's basically like a parrot. You're like feeding all this information into this parrot, and the parrot is basically like guessing, and it's right. And the parrot has some sort of CPU system, some sort of GPU system, where it can kind of guess what gives the most reward. What gives you the. That's basically it. And people are like coming up with like different approaches to like approach kind of like get away from this neural probabilistic method and kind of go in the in the realms of like biology, which like I'm not the smartest and like I don't know what's going on in the biology. Like computational linguist, what people are figuring out is computational linguistics is kind of a dead end. You can't really like we can humans. I mean, listen, humans can't even like comprehend every language. Humans can't even do it. The neural linguistic model that Noam Chomsky like made, it's heavily biased towards English. So English speakers could kind of like get the pass of like, oh, it completely makes sense. But you put Arabic, you translate all of this stuff with neurolinguistics with Arabic, yeah, it doesn't work anymore. It's like horrible. It's basically like guessing. So that problem of cognition, it's not even close to being solved. You can't even like kind of process the natural language. How can it like process the real world without being trained? Yeah, people like think unsupervised learning is just like what I mean. Like it's AGI, which AGI. I mean, it's in the realm. It's in the cybernetics category. It's not really like in the machine learning category, I assume, because machine learning one, it takes so much water to like train it. It's insane. Listen, am I saying that, like some of these ways of like approaching the path? Okay, anyways, deep learning, CNN, neural networks. Okay, whatever. What are they? I mean, that's not how humans learn.
Micrograph is basically
You
an
don't.
autograd engine. Autograd is short for automatic grading.
You develop a heuristics, and that's how humans learn. Like humans don't really like learn that way. Anyways, um, a common concept in ML that is closely related to weighted sample is sample weights. Weighted sample is used to select the samples to train your model with, with whereas sample weights are used to assign weights or importance to training samples. With higher weights affect your loss function more. What the fuck am I reading? Weighted sampling. Infrastructure and tooling for mlops. Huh. Feature engineering. What the fuck is feature engineering?
Data weighting.
Feature engineering is a very important process in the field of data analysis and machine learning. And I'm very excited to announce this new series of tutorials where I will be going over different feature engineering techniques and we will be writing Python code along with the exercises. With that, let's first understand what exactly is feature engineering. There was a study published by FBS magazine on what data scientists spend most of their time on. And from this chart, it was very clear that they spend majority of their time in data cleaning. Because in the real world, the data looks pretty messy as shown in this funny picture here. And you need to clean the data so that you can feed that clean data to your machine learning model. Machine learning model will not work if the data is messy. Even if you're not using machine learning and doing simple data analysis, you still need to clean data. So, data cleaning is very, very important, and that's where data analysts and data scientists spend most of their time, and feature engineering is something that helps you with data cleaning. Let me give you an example. Let's say you're studying home prices, and these are home prices in the city of Bangalore in India. To do the analysis on this, one of the things you can do is you can create a new column, which will be price per square foot. Just to kind of get a feel for your incoming data set. Now, this data set can be coming from the internet from a variety of sources, and it can have errors. Okay, it can have problems. So, by creating this new column, you're trying to analyze if you have any data errors. Okay? And once you have this new column, you can use either your domain knowledge. So, if you're a business manager that you're working closely with, say, in Bangalore, you cannot get a home at a rate of a price per square foot equal to 3,500 square feet. So, when you see this particular data point highlighted, which has a price per square foot as 500, it clearly looks like an error. Okay? And this error you detected by using domain knowledge. You can also use visualization. And by plotting this bar chart, this data point clearly comes out to be different than the rest of the data points. You can also use mathematics and statistics, where you can use techniques like standard deviation to detect this kind of special observation. Now, this data point here is called an outlier, and these three techniques.
Yeah, just basically be good, bro. Basically be decent, bro. Just be good, bro. Okay, weighted sample. I still don't know what a weighted sample is. Fuck me.
The random.
No, bless me. Bless me. In Python, you can do weighted sampling. What the fuck is weighted sampling? I don't get it. Like, weights in sampling? Is that what it is?
Welcome to the video series on understanding sampling and weighting in the demographic and health surveys. This video series
Data weighting by Spinnaker Research. Let's talk about data weighting in survey research. As a researcher, I want to make assumptions about large populations, but of course I can't interview all of the members of said population. Instead, I select a small section of the population that I can interview. This is called the sample. The sample I select
Goobity gookity gook. Juma juma juma. Googity googity gook. La guga jabo boo ama juana no. Contradictions like motherfuckers who like believe in it. If it gives them pussy, but like ropes and backbone or something. I don't know. I mean, it's funny because they're not leader. It's like actually when they talk to you, it's like liberalism. It's like retardation. But mistake. Aren't they like opportunistic kind of? Anyways, I need to go to this part of. It is a handbook, but it doesn't have any handle. The fuck? Isn't data engineering in here? Data distribution, monitoring. Okay, anyways. Dun, dun, dun. Bro, so funny. Racks and agents. I do want to work with racks a little. So let's go racks and agents. Fine tuning, RAG architecture. I wouldn't understand it though, so I need to like go from the three layers of AI stack. Anyways, let's go from here. Let's do this. Understanding foundation models. Let's do orderly because I'm an orderly man. Yeah. If I could use only one word to describe AI post 22, it'd be scale. The AI model would be behind applications like ChatGPT, Google Gemini, Midjourney, such as They are consuming non-trivial portion of the world's economic electricity. We are risk at running out the public availability of internet data to train them. Scaling up the AI models has two major consequences. First, AI models are becoming more powerful and capable and more task and enabling more people, teams leverage AI to increase productivity, create economic value, and improve quality of life. Second, the training large data models, LLMs, require data, compute resource, specialized talent. Only a few organizations can afford it. It also leads to emergence of model or service model deployment, but few organizations are made available for others to use as service. Anyone who wishes to leverage AI to build applications can now use these models to do so without having to invest upfront in building a model. In short, the demand for AI application has increased while the barrier of entry of building an AI application has decreased. This turned AI engineering, the process of building an application on top, readily available. This is one of the fastest growing engineering disciplines. Building the application on top of ML models isn't new. Long before LLMs isn't LLMs here? Huh? Prompt engineering. No, I mean AI evaluation methodology, understanding basic foundation. Okay, whatever. Um, AI is empowered by many applications, including the product recommendation, fraud detection, and churn prediction. While many principles of production AI application remain the same, a general new generation of large-scale, readily available models bring about possibilities and new challenges, which was the focus of the book. This chapter brings with a overview of foundation models, the key catalyst behind explosive of AI engineering, then discussing the range of successful AI use cases, each illustrating what AI is good for and not yet good for as AI's capabilities expand daily, predicting its future possibilities becoming increasingly challenging. However, existing application pattern can help to uncover the opportunities to today offer clues about how AI may continue to use in the future. To close out the chapter, I'll provide the overview of a new AI stack, including what has changed with the foundational models, what remains the same, and how the role of AI engineering today differs from the traditional ML engineers. Right aside of AI engineering, the foundation models emerge as the large language models, which is in turn originated as a large language model, which applications like ChatGPT, GitHub, and Copilot may have seen come out of nowhere, like the culmination of decades of technology and advancements. While AI language models have been around for a while, they've been only to be able to scroll today with supervise. This section gives you a quick overview of language model, and self-supervised means if you're not familiar with one of those language models encodes a statistical information about one or more language. Intuitively, this information tells about how likely a word to appear in a given context. For example, if you go to MyColorist dash, a language model that encodes English should predict blue or more than a car. I've heard, okay. Statistical nature of languages are discovered centuries ago, is it? No! Tung 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 sahur. Tung 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 sahur. Sherlock Holmes leverages simple statistical information to English to decode the sequence of mysterious stick figures. Since the most common language in English letter is E, Holmes deduced the most common stick figure must stand for E. The later on the cloths Shannon used to more sophisticated statistical decipher enemies messages during the World War II. His work on how model English was published, prediction of entropy of printed English language. Many concepts introduced in private, including entropy, are still used in language models today. In early days, language models involved one language. However, today the language models can involve multiple language, of course. The basic unit of language is token. A token can be characterized as a word or a part of a word like a partition, depending on model. For example, GPT-4 is a model behind ChatGPT breaks down the face. I can't wait to build an AI application into 9 tokens, of course, as shown in the figure. Not it's used like mapping and all of that. You could like do like a for loop and map all of them. And not only that, you could store all of them in a map, and all of them it's like kind of arranged in an ascending order, so to speak, and you can go and like access them however you want. You can encode and decode. That's like the good thing about it is, and you can like usually that's like a layer of transformer. You apply it to them. Whatever. Note that this example can be broken into two types, two tokens, can and can't. Can and can. It's more like hip hop syllables. Okay. Syllables. Okay. You can see how OpenAI model tokenizes the OpenAI website, of course. The process of breaking the original text into tokens is called tokenization. For example, the average token is around 3.4 length. So 100 tokens are approximately 75 words. Approximately 75 words. The set of all tokens model can work with models vocabulary. You can use a small number of tokens to construct a large number of distinctive words, similar to how you can use a few letters of alphabet to construct many words, of course. The model vocabulary has this tokenization method. Its vocabularies are decoded by many developers. There are two main types of language models: masked language models and auto-regressive models. They differ based on what information they can use to predict a token. A masked language model is trained to predict the missing token anywhere in a sequence using the context from both before and after a missing token. In essence, a masked language model is trained to able to fill in the blank. My favorite color is blue. My favorite color. Okay, it's a masked language models can predict the blank color. A well-known example for the in bidirectional transformer BERT. Of course, as of writing, mass language models are commonly used in non-generative tokens such as sentiment analysis and text classification. They're also used in body language, surprisingly. Believe it or not, body language, sentiment analysis. Like if someone like that's why they love to transcribe all of that to like kind of understand because words can reveal certain things. When you like see like one of those videos where it's like it's like an interrogation video, and that's like natural language processing right there because they use words to like kind of identify their intentions. It's like the victim and the killer accidentally says, "Oh yeah, the body's in." Yeah, I never said the body's in, but the detective never mentioned the bodies being in the fridge. You know what I mean? Stuff like that. You could like even work with like when you use certain words like we need to do this or I want to do this. I get to do this compared to I want to do this. Kind of like presents the I need. It's like a more like a duty compared to I get to do this. Right? Oh, it's like a fun little thing that I'm doing. So it kind of like it's you can kind of like, I mean, it's not like guarantee 100%, but it's like it's kind of probabilistic. It's probably if someone says, "I can't wait to get out of this job," they kind of mean it. I get to like leave this job. It's like then I'm more happy. Whatever, whatever. It's all probabilistic at the end of the day. So it's not really like this hard-coded rule in nature. If you use certain words, that means you mean it's like you can see this like anywhere. When friends talk to each other, they use certain words to like it has okay. Well, anyways, autoregressive language. An autoregressive language model is trying to predict a next token in the sequence. Okay, what is BERT?
BERT is one of those models that were based on the famous Transformers architecture and had a gigantic impact in the world of AI when they were first published. So in this video, let's see what BERT is, how it works, and how you can use
BERT explained in 60 seconds. Transformer neural networks can translate one sequence to another. Sequences can be words, like for example it can translate English to French. But these transformers weren't designed to solve language problems, and we need a lot of data for each language task. To solve this, we can stack a bunch of transformer encoders, and we get a bidirectional encoder representation of transformers, or BERT. We then want to pre-train BERT to understand language, and we can do this by training on two objectives of natural language inference and sentence text similarity. We then fine-tune this to solve other language problems. When fine-tuning, we don't really need to worry about requiring too much data, and this architecture is complex enough to capture patterns in language to perform well on general language tasks. Today, we're going to talk about BERT, so let's jump into it. This is the Transformer Neural Network architecture that was initially created to solve the problem of language translation. This was very well received. Until this point, LSTM networks had been used to solve this problem. But they had a few problems themselves. LSTM networks are slow to train, words are passed in sequentially and are generated sequentially. It can take a significant number of time steps for the neural net to learn, and it's not really the best at capturing the true meaning of words. Yes, even bidirectional LSTMs, because even here, they're technically learning left to right and right to left context separately and then concatenating them. So the true context is slightly lost. But the transformer architecture addresses some of these concerns. First, they are faster as words can be processed simultaneously. Second, the context of words is better learned, as they can learn context from both directions simultaneously. So for now, let's see the transformer in action. Say we want to train this architecture to convert English to French. The transformer consists of two key components, an encoder and a decoder. The encoder takes the English words simultaneously, and it generates embeddings for every word simultaneously. These embeddings are vectors that encapsulate the meaning of the word. Similar words have closer numbers in their vectors. The decoder takes these embeddings from the encoder and the previously generated words of the translated French sentence, and then it uses them to generate the next French word. And we keep generating the French translation one word at a time until the end of sentence is reached. What makes this conceptually so much more appealing than some LSTM cell is that we can physically see a separation in tasks. The encoder learns what is English, what is grammar, and more importantly, what is context. The decoder learns how do English words relate to French words. Both of these, even separately, have some underlying understanding of language. And it's because of this understanding that we can pick apart this architecture and build systems that understand language. We stack the decoders, and we get the GPT transformer architecture. Conversely, if we stack just the encoders, we get BERT, a bidirectional encoder representation from transformer, which is exactly what it is. The OG transformer has language translation on lock, but we can use BERT to learn language translation, question answering, sentiment analysis, text summarization, and many more tasks. Turns out all of these problems require the understanding of language, so we can train BERT to understand language and then fine-tune BERT depending on the problem we want to solve. As such, the training of BERT is done in two phases. The first phase is pre-training, where the model understands what is language and context, and the second phase is fine-tuning, where the model learns, I know language, but how do I solve this problem? From here, we'll go through pre-training and fine-tuning, starting at the highest level, and then delving further and further into details after every pass. So let's go deeper into each phase. So pre-training. The goal of pre-training is to make BERT learn what is language and what is context. BERT learns language by training on two unsupervised tasks simultaneously. They are mass language modeling and next sentence prediction. For mass language modeling, BERT takes in a sentence with random words filled with masks. The goal is to output these mask tokens. And this is kind of like fill in the blanks. It helps BERT understand bidirectional context within a sentence. In the case of next sentence prediction, BERT takes in two sentences, and it determines if the second sentence actually follows the first, in kind of what is like a binary classification problem. This helps BERT understand context across different sentences themselves. And using both of these together, BERT gets a good understanding of language. Great, so that's pre-training. Now, the fine-tuning phase. So we can now further train BERT on very specific NLP tasks. For example, let's say question answering. All we need to do is replace the fully connected output layers of the network with a fresh set of output layers that can basically output the answer to the question we want. Then we can perform supervised training using a question answering dataset. It won't take long since it's only the output parameters that are learned from scratch. The rest of the model parameters are just slightly fine-tuned. And as a result, training time is fast. And we can do this for any NLP problem. That is, replace the output layers
Ooh, ow, ooh. Solution architects. It's like, yeah, this thing. It's much more pragmatic than that. It's like that. Asking the most qualified person. Yeah, it's like, yeah, you should like work because you know, like, that's the value of that. That's the value of the feminist. It is what it is at the end of the day. Bah! Bah!
and then train with a specific data set. Okay, so that's pass 1 of the explanation on pre-training and fine-tuning. Let's go on to pass 2 with some more details. During BERT pre-training, we train on mass language modeling and next sentence prediction. In practice, both of these problems are trained simultaneously. The input is a set of 2 sentences with some of the words being masked.
Bro, it's so easy. That's what I realized. It's like actually so easy. It's a lot of time though. I need to um NLP. I need to learn a little bit of NLP. Um, kind of. It kind of matters. Okay, anyways. How deep do I need to go to ML engineering for mlops? I mean, ML engineering is like the base job, so don't really. Okay, anyways. Okay.